Alright, we're given this question for our chemistry: relationship between thermal energy, specific heat capacity, mass, and temperature change. So this question is given to us: what mass of gypsum can have its temperature raised 10 degrees Celsius by 6,000 joules? Gypsum is basically just a substance, so the specific heat capacity of gypsum is 1.09. So we're going to have to know that because of this formula right over here. Okay, so we're given this formula right over here. Basically, Q is the energy in joules, M is a mass in grams, C is the specific heat capacity in, it's just a unit, so for example, H2O, the specific heat capacity is 4.19 joules per gram degree Celsius. Basically means you have to have, it needs 4.19 joules to heat 1 gram of H2O to 1 degree Celsius. That's what specific heat capacity means, and this is unique to all substances. Delta T is one entire unit. Delta T is basically so here it is, I just wrote it down. Delta T is equal to Tf minus Ti. Tf is the temperature final of the entire substance subtracted by the temperature initial of the substance. So for example, we're given what mass of gypsum can have its temperature raised 10 degrees C by 6,000 joules. So we're just going to use this formula over here. Q is equal to MC delta T. Substitute Q for 6,000. Horrible writing, I know. The mass is unknown, so we're just going to keep it at x, and since it's all multiplying, we're just going to close the brackets. Multiply the specific heat capacity of gypsum, which you're going to have to find with a table you have with you, or just search it up on the internet. It is 1.09 in this case. For gypsum, it's unique to every substance. And since temperature or delta T is the difference of the substance, it's raised 10 degrees, so it's plus 10. So we're just going to keep it as 10. We don't have to do temperature final or anything, it just gives it to us. Now we're just going to solve this algebraically. X times 1.09 becomes 1.09x times 10 is 10.9, and divide by 10.9. 550.45 is the answer. So in the end, it's 550.46 grams of gypsum is needed to have its temperature raised 10 degrees Celsius by 6,000 joules of energy. That's how you do it. Now let's do another question over here. This one was fairly easy. Okay, so we're given this question. A 2.5 kilogram plank of wood is initially 22.2 degrees Celsius and receives 9.69 kilojoules of energy from a radiator. What is its final temperature? Well, first of all, we're going to have to look at this equation right here. Q is equal to MC delta T. Since Q is in joules, we're going to have to convert kilojoules to joules. Since mass is in grams, we're going to have to convert kilograms to grams. And the specific heat capacity of wood is given, and the delta T is not given, but it is since its initial is 22.2 and delta T is Tf minus Ti, we already have the temperature initial, so we're just going to have to solve for Tf through this algebra we're going to do right now. Alright, so let's just solve 2.5 kilograms to grams is equal to, since it's kilograms, it's going to be times 1,000, so 2.5 times 1,000, it's going to give us 2,500 grams. So we're going to have that as a unit of conversion over there, and we're going to have to also convert kilojoules. So 9.69 is also times 1,000, because kilojoules to joules is times 1,000, so the answer is 9,690. So we're just going to write 9.69 kilojoules is equal to, and now we're just going to solve for Q is equal to MC delta T. I'm just going to type this over here. Let's make Q is 9.69 kilojoules, which turns into 9,690. So 9,690 is equal to the mass. 2.5 kilograms equals to 2,500 grams. You always have to keep it into grams, so that is why we converted. We have to multiply, so I'm just going to put those in brackets. I'm just going to move this over here so you guys can see. The specific heat capacity of wood is 1.76. So 1.76 is going to go right over here. So since we're solving with this variable right over here, we're just going to put this in brackets and isolate TF as X. It's going to be X for TF minus the temperature initial, which is 22.2. So we're just going to close that. And this is going to be our equation, and we're going to solve for X. 2,500 times 1.76 is 4,400, and then we still have to multiply from X minus 22.2. Since this is algebra, we're just going to do 4,400 times X, and then 4,400 times 22.2. So 4,400 times X is 4,400X. And 4,400 times negative 22.2 is negative 97,680. Just going to put this negative 97,680. Then we're just going to isolate X, and I hope you all know how to solve for X. If you don't, then I don't know why you're in this video anyways, because this is a pretty advanced topic. X is equal to 24.40, and that is the final temperature it's going to be at, so we're just going to rather put that in degrees C. So yeah, this is your final answer, and that's about it. The only tricks in this is conversions and the specific heat capacity. There's nothing really to be careful of, because they gave you the table for specific heat capacity. For Q, for the energy, it's just energy in joules. Mass is in grams. Delta T is this formula right over here. So there's nothing really to get mixed up on. It's really just plug and play. And that's about it. Thanks.